That has an advantage from the nuclear reactions point of view. And if you take calcium, which is element 20, and want to end up in the region of around 114, that means your target is an actinide, and those that we have used, or that were used in our field, I should say, are highlighted in yellow, and they are deposited as thin foils on thin layers of, classically on titanium backings, and here you see a wheel, a target wheel that is rotating in the beam, and that dissipates the heat over a larger area. The diameter is 10 centimeters, and this was our hottest target, so to say, is Berkelium 249 with less than 1 year half-life. That was 700 gigabecquerel, and we use this for element 117 production and also for the search for element 119. Because 118 is not, right now is the end of the table, and it looks nice and compact and complete, but eventually I'm sure in a future RCEPS conference there will be reports on elements 119 and 120. Experiments are going on. It's given in an abstract of a later talk this week as well. When we come to chemical studies of these elements now, I take the table as it is known nowadays, and I can simply blank out the elements where no chemical studies are reported, and you get the impression that is quite funny. Why does it go all the way up to hassium? Then you have a break of 3 elements, and then you have 3 more, and the rest is empty. Now that is a combination of different effects. It is hard to produce 19, 110, and 111 with isotopes that are long-lived enough that you can perform chemical studies. Plus the chemistry and the groups where these elements are located is quite complicated. You can already see it from the lighter homologs like rhodium and iridium. They are not quite so similar, so what do you expect for meitnerium? It is not so clear. And historically, 114 has always been in the focus of nuclear physics. There was this island of stability concept centered around element 114, and also for the chemists, element 114 was very special for a very long time. And so the current focus is now clearly on those elements here. These are in the title of the talk. And we compare their behavior to that of their lighter homologs to sort of keep the spirit of Mendeleev's idea that in the periodic table, elements that are underneath in a given group share chemical properties. And so the questions we ask include whether flerovium is chemically behaving like lead, which the periodic table would suggest, which every normal chemistry student would answer in a test right away. What do you expect if you know nothing about flerovium? The answer will be, I look up at the table and I think it is lead-like. So it may come as somewhat of a surprise that there is a paper dating back to 1975 by Ken Pitzer from Berkeley that bears the title whether the elements 112, 114, and 118 are relatively inert gases, noble gases, so to say. Now, most people in this audience will agree that for 118, which is nowadays known as organeson, this may be a straightforward expectation, but if you scan the current literature, you find a lot of papers bearing titles like why element 118, organeson, the noble gas, is not noble and most likely not a gas. So this chemistry has not been studied, but theoreticians predict that this should deviate quite substantially from the trends. We will focus on elements where we do have chemical properties, and that is 112 and 114. So, what about Mendeleev? Is he completely off with the prediction that lead-like element would be underneath lead? So what I show here is the enthalpy of formation of monatomic gaseous elements given in kilocalories per mole. That is basically the energy that is required if you have a solid block of an element to remove one atom from that block. And that is an indication of the volatility of this element and of the forces that bind these elements together. And I highlight some elements that are in a given group. For group 14 we have silicon, germanium, tin, and lead, and that forms this line shown here. And there is no computation in this plot. This is purely experimental data. And you see there's a nice trend, so the periodic table seems to have some validity, but also it suggests this energy will go down as you progress down the group. And maybe even Mendeleev's table suggests that 114 should be relatively inert. So the energy that you need to remove one element, 114 atom, from a block of 114 is not so high. Now we cannot test that because we lack this block of element 114, but I will show you what we can do is we can take a single atom and put it on top of a different metallic block. And if you do this for a number of elements and always choose the same other element, maybe you get something that resembles this trend, which in fact is true. In group 12, there is element 112 that was also mentioned in that paper. You see this energy is very, very low, and so maybe there the assumption that this might be a gaseous at room temperature is best founded also in the principles of the periodic table. We have mercury, which is a liquid, down here. So, why are the super heavy elements interesting for the chemists? Of course, it's always fascinating to be the first person to study the chemistry of an element that has never been studied before. But there is more to it, and that can be traced back to the influence of what we call relativistic effects. And on this busy slide, I will start down here on the left-hand side, where you see orbital shapes that everybody is probably quite familiar with, and you see the S, the P, the D, and the F orbitals, where the shape is fixed by the quantum number L. Now, you may have heard that L is no longer a very good quantum number when you go to the heavier atoms and you move from LS coupling to JJ coupling. And what that really means is that L no longer fixes the shape, but J fixes the shape, and this may be very hard to read here as it is so small. What I plot here is a S orbital and a P orbital, and then I plot here another P orbital, where I give the quantum numbers L and J. L no longer is very relevant. We still call it an S orbital, but the shape is fixed by J, and J adopts the value of 1/2 for both of these orbitals, so they should have the same shape, which follows very naturally from that concept. However, if you think back as a normal chemist, what it means is that you have an S orbital, which is spherical, and you have a P orbital, which is spherical. And that is not something that you will have readily in mind. However, it computes out to exactly that. And so what happens then in these heavy elements is that the very high nuclear charge accelerates electrons that are in close proximity to the nucleus to very high velocities. They reach velocities of about 70% of the speed of light. In the simplistic picture of a hydrogen-like ion, meaning if you have just a core and one single electron surrounding that core in an S orbital. That means it's accelerated and it has a relativistic mass increase. The mass, the rest mass, is still the same, but the mass of the moving object is about twice as high. So you have an electron which is simply twice as heavy, simply due to the high nuclear charge, and that means it is attracted more strongly to the core, as follows from Bohr's model of the atomic orbitals. And that means that these electrons in such orbitals, they are attached more closely to the core, they are spatially contracted, these orbitals, and that means you need more energy to remove this electron, because you have to remove it from a core where it is closer than it would normally be at. That means you need more energy, so they are energetically stabilized. And the stabilization of these S orbitals, I would be able to point to the red line here, is not so large yet for gadolinium, which is atomic number 64, and increases for curium and goes up all the way to 114, of course. Now when you have these spherical orbitals, they shield this core quite well as far as the other electrons are concerned in orbitals that have a node at the position of the nucleus, like basically any other. So the 3/2, the 5/2, and the 7/2 share this feature, and in a more classical notation we would call them P3/2, D5/2, D7/2, and so on. And these are then expanded spatially, and that means energetically they're destabilized. You will need less energy to remove an electron from this. And if you do the calculations, on the one hand, putting in an infinite speed of light, we call that non-relativistic treatment, because you are always at the 0th% fraction of the speed of light. If the speed of light is infinite, then you would get this normal sequence. But you get these effects once you start to include the finite speed of light. And you see a splitting due to the spin orbit splitting, this P1 and P3 they start to split. That is more pronounced the heavier the elements become. You see those that are not 1/2 orbitals, they go up in energy due to this indirect effect that I have just explained. You see level crossings, and that of course is expected to mess up the chemistry to some extent. One would not necessarily expect that these elements behave exactly the same way as if there were no finite speed of light. So, yes. So let's go back. That was the paper title, are elements 112, 14, and 18 relatively inert gases. I plotted here the electron configuration, and so for 112 you will see this is closed shell. It's like mercury, except it's one row below, so it's not so surprising. This s orbital is filled, and that is contracted, so that should make it more inert. For 114, that will be a special story. For 118, of course, S2P6, it's a noble gas-like element that is also not surprised to be found in that title. And 114 is special, it has 2 p electrons, and in the lighter elements, they of course share different orbitals. They do not share one single orbital because of Hund's rule, but here in the relativistic treatment, you have this p1/2 spin orbital that can adopt exactly 2 electrons. So that is like a quasi-closed shell configuration. And that is also expressed in the energies of the outermost orbitals. Here I show those of the lighter homologues. You see this trend. For group 12, you have mercury, then you have thallium and lead, where the p1/2 is filled, and then the p3/2 is filled, and that is separated from the p1/2 by the spin orbit splitting, which is already a few electron volts, and for example can be seen nicely in the bismuth chemistry, where you see that there are some differences to the lighter homologues. When you go to the super heavies, these trends are much more pronounced, and 112 you see is completely filled as 1/2 orbital. It is expected to be very inert. Then in thallium we have one unpaired electron in the p1/2 orbital. Then you have this quasi-closed shell configuration in 114 before you then move up in energy due to the huge spin orbit splitting. And these elements then may be expected to be even more reactive than the lighter homologues. So learning all of this is quite hard for a chemistry student. Why is this element more reactive than the other one and the other one not, and so on. But if you understand the basic principles of these relativistic effects, it is quite natural to be expected like that. I would like to highlight this trend, which we will find later on. That is the energy positions of the most loosely bound electrons in these elements 112 to 115. So as I said, we do not have a block from which we can remove one atom, but we can say, let's take a gold surface. Gold is very nice, it's shiny, it's also chemically inert, it will stay shiny throughout the whole experiment. So we can make clean gold surface and measure the interaction strength of one atom with a gold surface. Then we approach the theorists and say, can you please perform the calculations for the strength of the binding of one element 114 atom on an extended gold surface? And then the theoretician will tell us, yes, we can do that. We make a very small approximation. We approximate this gold surface by one single gold atom. And then you end up with these dimer calculations, and you see the molecular orbital diagrams for the dimers in groups 12 and 14 for mercury gold, copernicium gold, lead gold, and flerovium gold. And these are the strength of these bonds. 2/3 of an electron volt for mercury. This is quite strong. This is an amalgam still. You see copernicium gold is more loosely bound. You see lead, a very strong bond. Lead is a heavy metal. It has nothing to do with a noble gas. And flerovium gold, lo and behold, adopts a value that is similarly low as the 2 elements in group 12. So this is the so-called the inert group, where there are paired electrons, no unpaired ones. And that also motivates to study flerovium, copernicium, and mercury in one and the same experiment to see if those minor differences can be really traced in the experiment. We also see group 14 is more reactive than group 12. Then we go back to the theoretician and say, thank you very much, that's very interesting, but our surface is not one atom. Can you not do any better? Can you not add more atoms? And then the theoreticians will say, yes, we can do this, and we can do cluster calculations where we simply increase the number of atoms of the gold surface until we see no longer a change in the energy if once we add more atoms. The theorist will call that a converged calculation, and then it looks like this. That is more complicated. The numbers are not exactly the same, but the trends are fully preserved. The differences, the relative differences, they are fully reproduced here. And nowadays, not even this is what the theoreticians can do as their best. They can do better, because here they take a rigid gold cluster and put an external atom on top. And in current calculations, they are embedded in this crystal pattern of gold, and the pattern relaxes in energy according to the extra element 114 atom that is embedded. And still, the trends from the dimer calculations are preserved. So we will expect flerovium to bind with gold. It's not a noble gas according to the calculations, but the bond should be very weak. You see the regularity of the surface here in the calculations that will become relevant in a minute. So, that is now a summary of these trends. On a gold surface, the experts can find some details of the calculations here on the left-hand side. And you see the lighter homologs, if you go from group 12 to 13, 14, 15, the lighter homologs show no pronounced kink for 114 because this P1 half shell closure is not yet so manifest in this light row. In the heavier ones, you can see it, and flerovium should bind much less strong than lead. We can not only use a gold surface, we can also use a silicon oxide surface, and you see the exact same trend. Some details are different, of course, but this really seems to reflect the energy pattern of the location of the orbitals of the most loosely bound electron. There is a shift between those two surfaces. Gold is more reactive than silicon, and if you put both into the same plot, you end up like this. And what that plot then suggests is that if copernicium hits a gold surface, it will be bound. If it hits a quartz surface, it will not bind. It would then simply travel over that surface without forming a chemical bond. Nihonium has an unpaired electron. This should bind even on quartz. 114 should not bind on quartz, but again should bind on gold. And 115 again is more reactive. So, when we want to do experiments with these elements, we first have to produce them, and we have to understand how to make them and what to expect in our experiments. I told you we use calcium-48 ion beams, and then we simply do a quite simple mathematical calculation. If we have 20 here and we want to have 114 here, we probably need 94 here, and that means we need a plutonium target to make element 114. And due to the curvature of the beta stability line, we want the most number of neutrons possible, so we take the exotic plutonium-244. We can go to element 95 from americium and then make element 115, or go to curium element 96 and make element 116. And this way, we can produce moscovium-288. This is well known from physics studies. More than 150 decay chains are known. We know how it decays, how many we can produce. It has a half-life of about 0.2 seconds. That is at the moment more or less the limit of what chemistry can do. That is a minimum time that we need. Flerovium is slightly more long-lived, on the order of 1 second. Once I add error bars here, these differences more or less disappear, so that is roughly 1 second. And you see those undergo alpha decay, so flerovium leads to moscovium, and 115 moscovium leads to nihonium, and this has about a 1 second half-life, again quite similar to flerovium. So we will get a few atoms per day, and we will look for these alpha decays, and even the daughters are undergoing alpha decay in many cases. So we get characteristic signatures with many alpha particles at specific energies, and that pattern needs to be fulfilled in order to say, yes, we saw one atom of element 115, but if you have 5 alpha particles in a sequence within 5 seconds and all the energies match, and you look at your background and calculate what is the likelihood that this is background, the number is then 10 to the minus 15 for this to be background. And then we say, okay, this is not background, we call this a real atom. Even on the level of particle physicists, we would be far above the 5 sigma threshold there. So let's look in detail now into the chemistry of element 114 from the experimental point of view. This is how we do the experiments. So we have the beam from the unilac hitting our rotating target wheel, and then we have a magnetic separator which deflects the beam and any transfer products that would show up as background in our spectra. And only element 114 takes a turn to then be focused by a set of 2 quadrupole magnets into a very small area where it will penetrate the thin foil and enter a small gas-filled volume. And from here the chemistry experiment starts. In this volume we have 1 bar of helium pressure and we stop element 114 recoiling from the target. And we have rapidly flowing gas, 1, 2 or 3 liters per minute, and force that through a narrow channel which we call our chromatography column. So we perform gas-based chromatography to study the interaction of one atom with a silicon oxide surface or with a gold surface held at room temperature. Here we call this device a compact detector because all these small squares here, they are individual alpha detectors. They're pin diodes, and we cover them with a thin layer of the element that we want to use as a chromatography surface. And then we simply wait and see where do we get those alpha decay chains, maybe in this detector here. Then we would know it has passed all the quartz covered detectors and was absorbed on the gold covered detector. We add a second compact detector that we can cool at the very end to liquid nitrogen temperatures to also be able to absorb noble gases like radon. When you have this system and you produce the lighter homologs, lead will end up immediately on the first detectors of covered with quartz because it is so reactive, whereas mercury does not interact with quartz. It travels to the gold and will be absorbed on the beginning of the gold-covered detector. Whereas radon as a noble gas will even travel over this and then be absorbed at the very end where the temperatures are very cold. And this way we can separate elements based on their chemical properties. And the interesting question now is, where does element 114 absorb? Here you see a few pictures. That is our target wheel. That is a photograph of this Tasca separator. It is about 3.5 meters long from target to focal plane. This is the small gas-filled chamber at the end, 3 by 3 centimeters square, more or less, a very small volume, and this is a photograph of the compact detector. To flush the gas through this chamber and then through the compact detector, we need about 0.3 seconds, so we have some decay losses for the short-lived ones, but the mere travel time through compact is 70 milliseconds, so this is fast even compared to this half-life, and we can really study where the elements will stop in the detector. Now, the first report of 114 chemistry experiments came from Dubna, from a collaboration led by a Swiss group, and 3 decay chains ascribed to 114 were reported, and 2 of those were reported to come from a setup that is quite similar to ours, from absorption at the very end near radon, and 1 atom absorbed at the beginning of the channel. Now what do you do if you have 1 here and 2 here? Well, they said this maybe did not live as long as it should have based on statistics and would have reached the end as well. So flerovium reaches the end, and that is indicative of a noble gas like Fish-Sorption type bond with gold. That contradicted more or less every current theory back in those times. And we performed our experiment where I just reported at RCEPS 2010 that it was performed, and we found 2 atoms and they stuck to the gold surface in the early part of the setup. So we said we cannot confirm a Fish-Sorption bond, we can conclude a metallic bond. And so there was some disagreement in the interpretation of what the chemical properties of element 114 would be. And what you do as a scientist is you take more data. So we took more data. Unfortunately, we only took 12 days worth of data in 2014, and we got 1 single decay chain, and it was exactly in the center of the radon peak at the end. So we were now more or less in a similar situation, 3 atoms, a 2-to-1 pattern. It's just reversed. We had 2 at the beginning, 1 at the end, and the other group had 2 at the beginning, 2 at the end, and 1 at the beginning. So we did not really know what to do with this, so we wanted to get yet more data, and in 2015 we did 1 month's worth of experiments. We got 5 atoms registered, And I will now discuss our total data set of 8 atoms gathered in 3 experiments that were, of course, distributed over several years, but always using the same setup, and verified by lighter homolog studies that the data can be merged into a single data set. So here is again a lighter homologs, and I show by the dashed line calculations of where copernicium would show up if it were there. That is known from prior studies. And this is our distribution of leurovium, 5 in the beginning and 3 in the end. And at that time you conclude, no matter what we do, we will apparently always get some in the beginning and some at the end. And this was the status 2015, and the paper you will see was published in 2022. It took us a really long time to come up with a model that can explain this pattern, honoring the chemical properties of leurovium the way they are predicted. The problem is, if you say this is a metal, you would expect the deposition pattern as given by this red solid line. You can nicely explain the beginning, but you would not expect 3 out of 8 at the very end. That should not happen. Or you can say, no, it is noble gas like the Swiss group working in Russia has published. You can nicely reproduce the peak at this radon position, but you should not observe a single one in the beginning, and certainly not 5 out of 8 lived shorter by orders of magnitude than what their known half-life would be. So this is somehow the problem. How do you reconcile this? We were suggested to incorporate into our model 2 different flerovium species. Some reacted to something, the others did not. Well, we are using industrial-sized gas cleaning to make sure we don't have any foreign gases. We just have pure helium and argon. With what should that thing react? It is predicted to be an unreactive element. None of the lighter homologs are showing any pattern of reactions. Why should the least reactive member then be the only one that undergoes a chemical reaction? We do not think that this is a likely explanation, though our data do not allow to rule that out. What we did is then that we said, you know, we spent now years looking at these 114 atoms, also the theoreticians. Maybe we should take at least a month to look at the gold surface, which is the other partner in the whole game. And the gold surface was analyzed by a variety of methods. We did XRD, and you see a pattern that is indicative of polycrystalline gold. You see the different facets of polycrystalline gold. And in the peak of gold 111, you see that you have some polycrystalline and you have some epitaxial gold. So this surface is by no means as homogeneous as what I have shown you from the calculations. You see the grain sizes, you see 20 to 50 nanometer larger grains, and then you see larger islands up to 100 nanometers. So you see grain boundaries, and for a theoretician, that's quite a mess. How do you model this and predict the interaction of 114 with this surface? But that is what we have in the experiment. The layer is inhomogeneous and is quite far from a pure gold 111 surface. So our interpretation says that, of course, you have to include in your explanation the fact that the gold surface is inhomogeneous. So it will have some sites that are not very reactive, only weakly interacting, and if flerovium hits the surface at that position, it will simply desorb back to the gas phase and be transported further down along the compact channel. At the very end, if only such sites are hit, it will adsorb because of van der Waals forces similar to radon. However, when it is hitting such a surface, it may start to wander on this surface, it may migrate, and it might diffuse eventually to a grain boundary, or put it more generally, to a more strongly reacting site, because the surface is heterogeneous also from an energy point of view. So our model simply requires you have a little interacting types of adsorption sites, and you have more strongly interacting types of adsorption positions. And then that will lead to a retention. And of course the beginning is warm, and their diffusion is fast, and so a good fraction of these atoms has reached such a site, and that shows that indeed you have some metallic behavior, because you see no retention of radon, regardless of which sites are hit, regardless of what type of diffusion is done, regardless of which grain boundaries you have. So flerovium is more reactive. However, it is not so strongly reactive some will reach the end, and the simulations predict that a peak should form at the very end. And that is currently our explanation for this bifurcated distribution of element 114. To summarize, flerovium is volatile. It reaches the detection system. That is the first condition. Not every element is able to do this. Unlike lead, it does not absorb on quartz. We see two peaks, and I have just explained to you where they come from. And the conclusion is that flerovium is a low reactive, volatile metal. It is not a noble gas, and the publication is by Sasha Yakushev, came out in 2022. So that was the easy elements. Because they are not so reactive, you can more easily bring them to a detection system than those that have an unpaired electron, 113 and 115. And if we come back to the calculations, I show you here predicted binding energies to gold surfaces, and we have now discussed those here, copernicium, and especially now flerovium. You see nihonium binds much more strongly, moscovium yet more strongly, and if you go to organezon, that's how the picture goes. So you have to invest quite a bit more to even bring those guys through that chamber that is covered by Teflon and put them into the detection system. That was found out in a story that is summarized here. The very first experiment reporting on element 113 was performed in Dubna, where the beam hit the target, and you had a quartz-covered chamber, and from that chamber you had a 4-meter-long tube leading to a detection system that is essentially similar to the one we are using. And 5 events were reported on gold at room temperature, but the background rate was very high. You see there's no magnetic separator. You get about a kilohertz of data rate from radon, which travels all the way to the detector. So to remedy this background problem, the second experiment in Dubna was performed behind the Dubna gas field recoil separator, and then again there was this long transport tube, 4.5 meters, but the stopping was no longer in a quartz covered chamber, it was in a Teflon chamber. And lo and behold, 0 events have been observed. The interpretation from Dubna put forward to explain both experiments was that in the first one, because of this quartz covered recoil chamber, the nihonium hydroxide was formed. And in the second experiment, elemental nihonium was present, and apparently this is able to reach the detector, and this is not. However, note that nihonium hydroxide has a much larger dipole moment than the elemental atom, and so this is predicted to be much less volatile. So why should this have reached the detection system, whereas the elemental species not? We performed our first experiment behind Tasca in 2016, and we did observe 0 atoms. And so we said, okay, the experiment would have expected maybe 3 atoms, that is at the brink of being statistically sensitive, but it looks like this element is really reactive. We have only 6 centimeter long tube and did see nothing. Dubna had 4 meters, 4.5 meters, and we think the chance of element 113 surviving a transport through such a long tube, that is basically 0. Even 6 centimeters may have prevented them from reaching the detection. So what we did is we wanted to build a setup with no transport line at all. And this is what we did. We took our compact detector. You see the channel here and here, these 2 half shells that are put together forming this narrow channel. And that is the exit of the newly built chamber, which leads directly into that channel. And so in a schematic picture, the blue thing is this stopping chamber with the gas, and then directly attached is the first channel made from quartz-covered detectors, and we add a second one with a gold covering, and we would expect 113 and 115 to stick to quartz, but 114 would travel through and reach the gold. This is the decay chain. You start with moscovium. We expected this to decay in the chamber largely because of the short half-life. We would then perform chemistry with nihonium and see this long decay chain ending with fission after about a day. So we did 2 experiments in 2020 and in 2021. In the first one we saw 7 decay chains. In the second one we saw 11 decay chains, which by our standards is a fairly high statistics experiment. And you see in 4 cases we were even able to see the alpha particle of element 115, moscovium, and in all the other cases we performed the chemistry with element 113. The distribution is given down here, so they absorb at the beginning more or less, but one atom of element 113 survived the transport over the whole quartz detector, so this interaction does not seem to be very strong, and it was then absorbed on the first gold covered detector. And this is the distribution pattern from the second experiment. Now, this is not fully analyzed yet. I cannot give you a detailed interpretation of what it means. All we can say right now is we see retention. If there were no retention, these atoms would have traveled far further down the chromatography system. So they are somewhat reactive, and the data analysis is ongoing, and probably at the next RCEPS conference there can be a talk about what it really means. So, but this starts to be an indication that this pattern with 114 being a quasi-closed electron shell in 114 being correct. If you want to go beyond, that is maybe now the last 2 or 3 slides, beyond moscovium, you have livermorium and tennessine. You may have seen the half-lives drop to the level below 100 milliseconds, and our technique is not fast enough for that. So what we are doing is we are exchanging the slowest piece, which is the stopping chamber, and replace this by a gas cell that is fitted with electric fields that drive out ions through a funnel structure into the mini-compact. And this was successfully tested with short-lived mercury, astatine, and francium isotopes at Texas A&M University and at GSI, and is published as part of the thesis of Stefan Götz. So we were able to achieve about 50 millisecond extraction time using a gas cell that was simply available from prior work, not optimized for chemistry, but it showed that the potential is there. And we could also see francium, which we could not see with a more conventional system. So also very reactive elements can be observed. And now we are building a dedicated high-pressure cell at GSI as part of the PhD work of those 2 gentlemen down here. The first piece has arrived at GSI. This is the funnel type structure. And with this, we hope to be able to tackle chemistry of 116, maybe eventually 117. And for 117, we have already studied the production. We know the production rate, we know the decay properties, and that was taken as a collaboration picture. And you see our eminent chairman is an honorable member of our 117 collaboration. With this, I'm at the end. That is what I have discussed today, the chemical studies of the super heavy elements, elucidate the structure of the periodic table in the realm of the heaviest known elements. I have shown you that element 114 is a low volatile reactive metal, and that nihonium and moscovium 113 and 115 are more reactive than copernicium and flerovium, and the interaction strength is being evaluated. That will come forward in a future conference. We are preparing for yet heavier elements. Also there, we hope to perform chemistry experiments in the next years once this setup is ready. With this, I'm at the end. I thank you for your attention. Looking forward to questions you may have.
Yeah, thank you, Christoph, for this very nice overview of these very exotic elements most of us don't get to deal with. Are there questions from the audience? Yes, please.
So you say current limit is 0.2 second to do the chemistry, and you also mentioned about some setup. Where will it take you? I mean,
what we have experimentally proven as a nation of a physical separator like TASCA with this buffer gas cell with electric fields and then a chemistry apparatus is 50 milliseconds. There is a dedicated setup that was conceived and where model calculations have been performed, where the pressure inside the cell is much higher and the gas flow dynamics and the electrical field performance should lead to a time below 10 milliseconds. Whether this really turns into reality, we will see, but the perspective clearly is it will be fast enough for 116 and 117.
okay. And another basic question. So I was missing that you are basically looking at the interaction between the gold surface and, but that should be pretty fast. So why even we will require 10 millisecond? And it's because you are throwing the system?
So we produce these atoms when the beam hits the target. They fly out with the momentum of the beam through the separator and they reach the focal plane after about 1 microsecond. Then they are stopped in this gas-filled volume. This gas-filled volume is flushed with about 1 to 2 liters per minute. And that takes about 300 milliseconds to flush a volume of this size with a gas of this flow rate to put them into the detector. So that is the time-limiting step at the moment, this stopping cell. That is why we replace exactly that part with a faster cell.
Thank you. It was very illuminating talk.
Thank you.
So, are there any more questions?
Thank you. Very interesting talk. So you are relying on calcium-48 for all these experiments. Do you have any concern about the availability of calcium-48 in the coming years?
Yes, we have very strong concerns about this. I do not have the slide here. I could show you how the chart of nuclei in the heaviest region looks if you have no calcium-48. It stops at 112 and then 113. 113 was made in Japan. Hirohaba may discuss it. 3 atoms over the course of 9 years using a zinc beam. This is not very attractive for chemistry experiments. So for us, for all purposes, it stops at 112. You cannot make any of the heavier elements if you have no calcium-48. And at that time, we do not have access to calcium-48 because of the war. So there are intense discussions going on in Europe how to remedy this situation, but at the moment this is unsolved.
You said that there is no other way. In the early times, people were trying to think about this hot fusion or things like that. Is there people looking at that again, or this is really not a good way to go for that kind of experiments?
Well, with hot fusion you probably mean light beams on actinide targets. Now we have progressed to a level where the elements that you want to produce are so heavy that this light projectile is calcium-48. So this is hot fusion reactions, and this is the way to make them. And any other way has not been successful. Can be seen from the fact that no element 119 has been reported. Because if we could use calcium-48, we would simply use an Einsteinium target, and I'm sure if that were possible, element 119 would have been discovered. But there is not sufficient Einsteinium coming from, example, from Oak Ridge to make a target. So we need to use heavier beams. And we did studies in Darmstadt to search for 119 and 120. There were studies performed in Dubna. There are other studies ongoing. And so which reaction exactly to pick is one of the not fully solved questions. Different labs have different strategies how to make new elements, but none has reported success to this date. So which element you pick instead of calcium-48 is not fully solved. And certainly for these that I have shown, no other projectile has led to the production of one of these elements. The production rates are expected to be much lower, so you're not speaking 3 per day, but maybe, I don't know, 1 per month. That makes a big difference.
Okay, one last question, please, in the back.
Yeah, so you said about the lifetime of those things for doing the chemistry. But is there any limitations on the number of atoms that are produced to do the chemistry?
How do you mean this?
This number of the production rate or production number of
the 3 per day. That is basically what is achievable with current technology. So you take current beam intensities, you take current target technology.
No, my question is there limitations on doing the chemistry with the number of elements that you have produced?
So if we would get a higher production rate, you mean?
No, when you're doing the chemistry, is there any lower limit that you cannot do on the number?
Yeah, well, the statistical significance will drop. If you have only one, you can debate for a very long time with a referee what it really means. It could be bad luck because it lived only a tenth of a half-life or 200 times a half-life. It might not resemble a true distribution. So I would say experiments where I know of that they were later confirmed usually had about 5 atoms at least. So we have 8 now for element 114, and one would ideally do an experiment with 10 times more. Normally you need an order of magnitude more to learn more, but we already needed about 2.5 months of beam time. So that would translate with current technology to about 2 years of beam time. So we will see if in Dubna with the super heavy element factory the production rate is going up, if they can report something, this we don't know. But below 5 it starts to be challenging to draw conclusions that you will be able to defend later on when there is more data.
Yeah. Thank you.
Okay, so let us thank Christoph again for this nice presentation.